Alright, so the last part of equilibrium we're going to talk about is determining the concentration of reactants and products at equilibrium. So if we think about what the equilibrium constant tells us, our equilibrium constant gives us a ratio of the concentration of products over the concentration of reactants. And the numerical value for this tells us whether we have more products or more reactants at equilibrium. And we can use this value to determine how much we have at equilibrium. But what if we start with 1 molar A and 1 molar of B in a reaction that produces product C? How much C should we have at equilibrium? Well, if our K equilibrium value is 3, then we can try to figure this out. Alright, so first let's say that we want to calculate our Q value. Well, if we have no products, so C is 0, our Q value should be 0. Okay, Q is less than K, so we know we're going to be making product, we're going to be making C. How much C can we make? 1 molar, because we have 1 molar A, 1 molar B, so our stoichiometry would suggest maybe 1 molar. But 1 over 1 times 1 is not 3. So would we make 3 molar with the C? But where do we get 3 molar of C if A and B were only 1 molar? Alright, so our stoichiometry doesn't go with our equilibrium with that kind of logic. Our stoichiometry says that 3 molar of C formed from 1 molar A and 1 molar B would not work. We couldn't do that. But if we only made 1 molar of C, that wouldn't fit our equilibrium. So we have to consider both stoichiometry and our equilibrium constant K. Alright, so let's go back to our idea that Q is 0 at the beginning. We have no C, we have 1 molar A and 1 molar B. Okay, so we're going to be making product, but we don't know how much. So the amount of product that we're going to make, we're going to call X, our variable. And one other thing we need to remember is when we produce some amount of C, we have to use up some A and some B. So the A and B values will be going down. Alright, so we're going to use what's called an ICE table to calculate how much we're going to have. So we have our balanced equation at the top, A plus B goes to C. And down the side we have 3 different stages of our reaction. The initial amounts, so the concentrations that we start with, so A and B are both 1 molar and C is 0. The second row is going to be the change. What is going to happen as our reaction goes to equilibrium? Since we associated that value with X, A is going to go down by this X value, B is going to go down by the X value, and C will be increasing by the X value. Then on the third row, this is our equilibrium row, where we're going to take our initial minus our change to get our equilibrium amount. So 1 minus X for A, 1 minus X for B, and then C is 0 plus X. Alright, now that we have our table set up, we want to take our equilibrium row, which represents our concentrations of A, B, and C at equilibrium, and put them into our K equilibrium expression. So remember, our K equilibrium expression is really looking at the concentration of the product at equilibrium divided by concentrations of reactant A and reactant B at equilibrium. And now we have expressions for those. So C is X, and A is 1 minus X, and B is 1 minus X, and this whole expression then has to equal our K value of 3. Alright, so now we can solve for X. We just have to do a little bit of algebra. So in this situation, we're going to FOIL out the 1 minus X to get 1 minus 2x plus x squared on the bottom. We still have x on the top, still equals 3. Then we want to multiply the bottom part of our ratio over by the 3. So 3 times our FOILed out expression is equal to x. Then distributing the 3 and collecting terms, we get a quadratic function. Alright, so our 3x squared minus 7x plus 3 is our quadratic function. And then we can solve this by using the quadratic formula. Or if we could, a graphing calculator. So over here, this is the quadratic formula, in case you don't remember it, where we just need to know the values of a, b, and c and fill them in. And then we will get two values of x because we have an x squared value. Alright, so when we solve this, here's our two values of x. 1.768 or 0.5657. So which of these are we going to use? What's going to make sense with our ICE table? Well, if you look back at our ICE table, I'm going to move back to it, our x value needs to be less than 1 because we can't use more a and b than we started with. So the amount of c that we make has to be less than what we had for a and b. So we're going to pick the smaller value that is less than 1. This larger value would give us our negative concentration, which we can't have. So if we plug the smaller number back into our ICE table, we can calculate our value of a, 1 minus 0.5657, and calculate the value of b, which is the same thing. So they're both 0.4343 molar. At equilibrium, this was what will be left of a and b. And then c was just equal to x, which is our 0.5657. So this would be the amount of product that we make. And if you plug this back into our expression of c divided by a times b, you will get our K equilibrium value of 3. Alright, so here is the steps that we went through in order to solve this. We need a balanced equilibrium expression or equation. We need to determine the Q value. Which direction is the reaction going? Toward products or toward reactants? We need to set up our ICE table with our balanced equation, and then look at our initial and change values. Equilibrium rho is just initial minus the change. Filling in our equilibrium values for the K equilibrium expression, and then solve for x. Once we know x, we can plug that back into the equilibrium row and find our concentrations. Now, from the example, you saw that we ended up with an x squared value. Frequently, this is going to be the case, and it can actually get worse. X to the third or x to the fourth values. So we're going to talk about a couple of assumptions we can make to try to make the math easier. Alright, so the first assumption we're going to look for is this idea of perfect squares. If we can get rid of the x squared function and just have x, it's going to make it easier to solve. Second assumption we're going to look at is looking at the value of k. If our equilibrium expression value was very, very small, we're not going to be making a lot of product, and we might be able to ignore parts of our expression. And then, of course, our third option, using the quadratic formula to try to find x. Alright, so we're going to look at assumption 1, looking for perfect squares. So here's our example. 2.5 moles of HI injected into 10.32 liters at 25 degrees Celsius. What is the concentration of H2 at equilibrium? Alright, here's our balanced chemical equation, so we have that part. We know the K value. Alright, so we have that. And here's our expression for Kc. H2 times I2 over our HI squared, set equal to the K value. So how do we find out how much H2 we have? Alright, we need to set up our ICE table. Now one thing to look at, ICE tables are only for molarity. We're looking for concentration values. So I can't put moles on my ICE table. I can't put volume on my ICE table. I need to find molarity. So we need to calculate the molarity of HI going into the ICE table. So 2.5 moles divided by 10.32 liters. Alright, so when we put this on the ICE table, 0.242 molar comes from doing that calculation. 2.5 moles divided by 10.32 liters gives us our 0.242 molar. So that's our initial concentration. We have zeros for our products because we haven't made any products yet. Then on our change row, we have minus 2x. Now the 2 comes from our balanced chemical equation. Any coefficients that we have in the equation need to be pulled down to the change row as well. So if I have 2HI, the change row is minus 2x. H2 and I2 are just plus x because their coefficients are 1. Alright, then on the equilibrium row, pulling everything down, 0.242 minus 2x, and then x for each of our products. Alright, so the next thing we want to do is plug this in to our K equilibrium expression. So H2 times I2, x times x, over 0.242 minus 2x squared. Remember, our HI was squared from our expression, so we have to square it. Now we have x squared on the top and 0.242 minus 2x squared on the bottom. So this is what we call a perfect square. The top is squared, the bottom is squared. So we can take the square root of the entire thing to simplify our math. When we do that, we need to take the square root of what's on the other side of the equal sign as well. So the square root of the K value. So now we're left with 1x over 0.242 minus 2x is equal to the square root value of our K. Now we have a simplified expression. We only have an x value instead of an x squared, so this makes it easier to solve. So we get one answer for our x that represents our equilibrium value from the table. Now if we look back at our table, H2 is just x at equilibrium. So once we know x, that is our H2 concentration. Alright, our second assumption has to do with K being very small. So we're going to see what happens when our K equilibrium value is a very small number compared to our concentrations. Alright, we have 0.5 moles of I2 in a 2.5 liter vessel. What are my concentrations of I and I2 for the reaction? Alright, so I have I2 being converted to 2I. There's my balanced equation. Here's my K equilibrium value. Alright, very small, 10 to the minus 10 at 600 Kelvin. My expression, we have I squared over I2 equals our K value. So again, we need to find our molarity for our I2, so our initial amount. We have moles over liters, so that gives us 0.2 molar for our ICE table, 0 for our products. Now our change is minus x. Our products are plus 2x because we have a coefficient of 2. And we're putting it together, we get 0.2 minus x for our I2 and 2x for our I. Alright, so now when we plug this back into our K expression, we're going to have 2x squared, because remember our I was squared, over 0.2 minus x. Now this is not a perfect square because the bottom is not squared, so we can't take the square root. But if we look at our value of K, we notice this is a very, very small number. If we have a very small K value, that means our reaction is mostly reactants. It didn't go very far to products at all. So if our reaction is not forming very many products, what do we know about this X value? It has to be pretty small because we're not making very many products, so we're not going to see a big change. So what is 0.2 minus very, very small? It's still 0.2. So if our K value is very, very tiny, our X has to also be a very small number. So subtracting it from a much larger number doesn't really change anything in terms of significant figures. So we're going to ignore this minus X. It's too small to matter. It's negligible. So we have our 4x squared on the top divided by 0.2 on the bottom, because we're going to take off the minus X, equals our K value. Now since we only have an x squared value, this is easier to solve. We can multiply by 0.2, divide by 4, and then take the square root. Alright, so here's our x value. And x is very small. So we can plug this back in up here and say 0.2 minus this x value would still pretty much be 0.2. Alright, so that means at equilibrium, our I2 has not really changed that much. It's still 0.2. Very little of it was converted. Here's our I amount, 2x. So we multiply our x value times 2. 7.67 times 10 to the minus 6 molarity. So very little I is created. So if the K value is very small, we can usually make the assumption that x is very small, and we can ignore any adding or subtracting of the x value. Now let's look through the same example, but instead of having a very small K value, we have one that's much larger. Alright, so we have our 2x squared over our 0.2 minus x. But since K now is not incredibly small, it's on the same order of magnitude as our concentrations, we can't say that x is a very tiny number now. Okay, our reaction is going somewhat to products, so we can't make any assumptions about x. We just have to stick with it. Alright, so we're leaving the minus x on the bottom. Now we have to multiply over, we have to FOIL or distribute out our 0.209, and we get a quadratic function. Alright, and here we can use our quadratic formula to solve it, or a graphing calculator to find the intercepts. Alright, so here's working out the quadratic formula over here, filling in our A, our B, and our C values to get our x. Alright, so again we would get two answers because we have an x squared, but only one of them will make sense. This is the x value that makes sense with our ICE table, had to be less than 0.2. And when we plug it back in, 0.2 minus 0.08 gives us our concentration of I2 that's remaining, and 2 times our 0.08 gives us the amount of I that we created. Alright, so when working through these ICE tables, you need to pay close attention to where your coefficients are. Make sure you know which direction you're moving in, toward reactants or toward products, and check your math. Alright, some of these can get very complicated in terms of the math, and it just means there's a lot of room for error and making mistakes, especially with a quadratic formula. So just be very careful, work through your questions slowly, methodically. I'm not going to give you really hard, complicated math on the test. Definitely not going to give you an x to the third or something worse. So look for the assumptions. Look for making your math easier. Alright, in the next video, I will show how to do some of the ICE tables.